Last time we started getting into chapter 1, we talked about matter. We talked about sort of different states of matter as we transition from one state to the next, sort of what those transitions are called. So remember, as we go from solid to liquid, that is melting, liquid back to solid, that is freezing, liquid to gas is evaporation, and backwards there, gas to liquid is condensation. We have sublimation that takes us from solid all the way to gas, skipping the liquid phase. And we have deposition, which takes us from gas back to solid, skipping the liquid phase as well. Remember that as we go from solid to liquid to gas, those are all endothermic type processes like we talked about. Heat and energy needs to be put in to sort of do those changes of state. As we go from gas back the other way, liquid to solid, those are all processes that require energy to be released, which is exothermic, is what the process is sort of referred to when we release energy. And we also talked about, I believe, sort of elements, compounds, molecules. So remember that a molecule is sort of, as we talked about, like a basic definition of just simply two atoms, two or more atoms together. That can be two atoms that are the same element. That could be two or more atoms that are different elements. But that is the basic definition of a molecule. Remember that some elements do come as diatomic molecules. So things like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they all come by themselves, uncombined, but they do come basically as twos. So like H2, N2, two atoms of each of those. Remember that those guys are molecules and they're also elements because they only contain the same element involved. And that's different than a compound. In a compound, we have two or more elements involved. So we have atoms of two or more elements. So something like water, H2O, that is hydrogen and oxygen involved, which makes it a compound. It also makes it a molecule because there's two or more atoms together. We talked about, I think as well, if I'm not mistaken, I hope it's this class, so that was homogeneous and heterogeneous mixtures. And remember, a homogeneous mixture is one where we mix two or more pure substances together, and they basically do all sort of mix, they dissolve. It really looks the same throughout, so it looks like one phase when we look at it. And that's different than a heterogeneous mixture. That's when we mixed two or more things together, but we still do see separate phases. So you see different layers and stuff like that. So like sand and water, I think we talked about the other time, that's heterogeneous. You can mix it all day. You'll still see the sand in the water. And obviously something like salt water, if you put some salt in water, it will dissolve. And if you look at it, it will just look like water. So that is a homogeneous mixture. The key with our homogeneous and heterogeneous mixture, regardless of the type of mixture, remember that those are really physical changes. We basically can still get all of the components of the mixture back if we do some type of physical process, like filtering, like heating it up and things of that nature. So I think we talked about sort of heating up the salt water, that'll evaporate off the water, which we could collect the water and would have the salt left over when we're done evaporating off all the water. Something like the sand and water, we could simply just put it through filter and a filter paper. The solid will get trapped on the filter paper, liquid will go through, and we get both of those things together. So when we talk about physical changes, remember that a physical change and what you start with and what you end up with is fundamentally the same thing. A chemical change is when we start with something and end with something that has fundamentally changed to something new. The key of that is you cannot get back your original sort of components by any type of physical means. Usually a chemical change is a chemical reaction. So, if we take hydrogen gas and oxygen gas and put it together, we get water. But you could take that liquid water and do a whole bunch of stuff to it physically, like heat it up, freeze it. You'll never get the hydrogen gas and oxygen gas back unless you do some type of chemical change to it, like running an electrical current over it where it would break it apart. We finished up, I think, started to talk about measurements and the idea of units. Remember, there's two different types of units that we come across. So we started talking about measurements, and again, remember that there's basically English sort of measurements, and there's really the metric system. And for the most part, in chemistry, we come up with sort of what is referred to as the SI system of units, which is really based off of the metric system. And it's really important to include units, obviously, when we do things. Gives people an understanding of really what the meaning of the value is when you look at it, or you take a measurement, what that number really represents. We finished up, I think, talking about measurements, how to properly take measurements. So remember that, when you do take a measurement, the key is to really look at the scale you're dealing with. And let's just say we had this ruler here. And again, if we were taking some type of measurement, as we talked about last time, the first two things you really want to determine when you're using any piece of equipment is really what the scale represents. Now, whenever you take a measurement, there's always going to be some degree of uncertainty associated with that measurement. And when we look at this particular scale, as we saw last time, the really major units is the big units there are really 1 centimeter. And if we start counting after the 1 there, right about there, and go all the way to the 2, there are 10 markings in between. So if we kind of divide that up, we know that the smallest markings represents 0.1 centimeters. So there should always be numbers that no matter who takes a look at it, everybody should agree. So everybody should at least agree this is 1.1, 1.2, 1.3, 1.4, 1.5. So it's at least 1.4 there. And it's very customary to record all of what are sometimes referred to as all the certain numbers. And again, those are numbers that no matter who takes a look at it, everybody really should agree upon that it's at least that much in terms of those numbers. But now, obviously, when we look at our marking there, we could see, it's not really 1.4, not really 1.5. There is some degree of uncertainty where we really has to make sort of an estimate. And again, you may look at that and visually go, kind of divide that part up and go, I think it's halfway there. Maybe it's a little bit more than half. So for example, we'll just say it's a little bit more than half and put a 6 there. And we obviously would want to include the units. As we talked about last time, when we take a measurement such as that, when we record basically all the certain numbers plus the first uncertain number, that really is, what represents the significant figures in a measurement. So obviously this particular one here would have 3 significant figures. All 3 of those would be significant in this particular case. With the estimated digit or sort of uncertainty or estimation obviously happening in the last significant figure. So that's really an important thing. Sometimes people are asked a question like, where's the uncertainty in this measurement, or where's the estimation in a measurement? And a lot of times people will just pick the last number written. It's not necessarily always the last number written, although 9 times out of 10 it actually is. But it is really the last significant figure is really where the uncertainty lies. And that may not be, and we'll look at something a little bit later, I think, that may not actually be the last number that is written. We also talked that obviously if we take something like a liquid, right, we have a meniscus that should have the curvature of the liquid in the solution. And we always want to read from the bottom of the meniscus. And remember that, when we look at the volume, we want to take that bottom of the meniscus sort of reading. So when we take a reading, in most cases, we can take the reading to one more place to the right of the smallest marking. So what we see here is obviously the smallest marking in my above example was to the first decimal place. We're actually able to take the reading there to the second decimal place. It's not 100% always like that, but in most cases you can do that. So for example, if we had a liquid, and call the guy 30. And if we had some type of liquid in there, maybe we have like a, maybe wake up. All right, we'll just put it here then. That curvature. So if we were to take our reading, we would want to read obviously from the bottom of the meniscus. We would look at here and we would see that in terms of the big markings, that is 10 milliliters difference between 20 and 30. Again, if we count the lines that are going up there, that is 10 lines, which means in this case, each smallest marking is how much? 1 milliliter in this case. This guy would be 21, right? 22, 23, 24, 25, 26, 27, 28, and 29, and then 30 going all the way up there. So again, we would follow the same rule here. Again, no matter who takes a look at it, everybody should hopefully agree it is at least 24. Again, we're going to make an estimate there from the bottom of the meniscus, which is, in this area here. And we may say that it is halfway there, and 24.5 milliliters would be the correct one. Again, the smallest marking is the whole number, which means we typically could go one more place to the right, which is where we did there at 24.5. That would have how many significant figures? It would have 3. Our uncertain digit would be the 5, right? That's right here. Yes, sir. We're going to talk about the rules for doing calculations with significant figures, and really that's based on sort of they're really based on like your worst measurement where the uncertainty lies. So if you're multiplying, for example, 2 numbers and you're doing a number like what we have there, and maybe like a whole number, the uncertainty in this measurement is actually here, and that's really what determines your overall sort of calculation. Is really your worst measurement. You're only as good really as kind of your worst measurement. So when we think about sort of doing the calculations, that one that has the worst sort of estimated digit or smallest is where it lies to. To answer your question in terms of, I don't know if I specifically will ask something like that. I know it's a lot of times in like labs, they sometimes ask that, like, here's a number, what is the estimated digit? Or maybe some homework may ask that. And when you look at a number or measurement and you're asked, where's that uncertain digit? You want to first determine, the first thing you want to determine is how many significant figures there are. And it should always be the last significant figure that's there. And again, a lot of cases, it will be the last number is actually written, but not 100% of the time. So, yeah. Yep. Other questions? So let's say we had something like this. Again, sort of a graduated cylinder, and we had sort of a meniscus there. Now, when we look at this, we still have, in terms of our big numbers, right, 10 milliliters. If we count the lines starting here, there's 1 line here, 2, 3, 4, and then 5. That means each of these lines represent how much? Actually represents 2 milliliters, right? In this particular case, the smallest marking. Which means if we look at this, this is basically 22, 24, 26, and 28. We find ourselves actually in this case now between 24 and 26. What is between 24 and 26? It's actually 25, right? In this particular case, the best you could do because of that scale is probably go to 25. There's not enough room between 24 and 26 to figure out where 24 ends and kind of where 25 begins. There's really not enough room between those two. So this is a kind of a rare occasion that, you might have a scale like that where you actually can't go one more place to the right. But in most cases, probably 9 times out of 10, if you take your reading to one more place to the right of the smallest marking, you'll be in good shape. But this also is why we should always look at the scales, even if you're 2 people are using the same equipment in a sense. For example, both are using 10 milliliter graduated cylinders, maybe made by somebody different. The scales may actually be different on them, even though they're technically the same sort of piece of equipment. So it's always good to make sure that you look at those things. Any questions on that there? Okay. All right, let's see. So here's our fish, good fish there. We got two different scales up here. If we look at the top scale here, we can see that the big units here are 10, I'm assuming centimeters. But actually there are no smaller markings on the very top scale here, which means the big and the small markings are basically the same thing. So our big markings or small markings here represent basically 10 centimeters. So the best we could do is really make an estimate here of 53 centimeters. That would have how many significant figures? Would have 2, and the estimated digit here would be the 3. And basically, again, if you think about it, you know, you're basically saying, I think it's 53, but maybe it's like 54. Maybe it's like as low as 52, where we have sort of that last digit having a little bit of flexibility and uncertainty in it. And if you look at it, you know, that is probably the sort of correct range as to, you know, what we're looking at. Now, if we have this scale down here, which is again, big markings like we were doing on our previous one, there is 10 centimeters. There are 10 markings in between, which means again, here on the bottom, our smallest markings are 0.1 centimeters. And we find ourselves looking at this and we can see 51, 52, and 53. I'm sorry, that is 10 centimeters, and that would be 1 centimeter each. My bad. 1 centimeter there. I'll learn to count soon. That's 1 centimeter. So the 10 markings, each of the smallest markings would be 1. That would be 51, 52, 53. And again, you can see it's just a little bit beyond the 53. So we do record 53.5 in this case, which has 3 significant figures, which this guy being our estimated digit. And again, basically when we say that, we're basically saying I would think it's 53.5, but maybe it's like 53.4, maybe it's 53.6. Again, if we look at sort of where that marking is, that really does sort of match up with what we do see. Now, what happens if we did have, say, something that lands exactly here? We'll go back to this scale here. All right, so let's just say we had something and it's like dead on-ish, that line right there. All right, so same scale here. We have 1 centimeter as our big markings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings in between. Now this one is really 0.1. Now, when we look at it here, this would be 1.1, 1.2, 1.3, 1.4, 1.5. So we feel it's like right on that 1.4 number. Do I record 1.4 centimeters or 1.40 centimeters? Which one should I record? Or is there a difference in terms of what I record? You should record 1.40. And there really is a difference in those numbers. So for example, if we took 1.4, how many significant figures would that number have? It would have 2 significant figures, right? Basically, the uncertain digit here would be the 4, right? Which basically when we're saying here is I think it's like 1.5, or maybe it's like 1.3, 1.4. And we could clearly see it's actually like nowhere even near those numbers here, right? And that's not the greatest measurement. When we look at 1.40 centimeters, that has how many sig figs? Would have 3 sig figs. The uncertain digit there would be, it would be the 0 here at the end, right? It would be our uncertain digit. And that means that we're basically saying, I think it's 1.40, but maybe it's like 1.41, maybe it's 1.39. And if we really look at sort of where our measurement is, that is correct based on the scale that we have. So you never ever want to lop off numbers, or if you feel it's not important, it really is important. If you get rid of the 0 in this particular case, you just made yourself a pretty crappy measurement, right? It made it a lot worse than it should be. This is really what it should be. So in a situation where you feel something is like dead on a number that you're taking a measurement, if you have the ability to go one more place or whatever it may be, you should add a 0 there to maintain the proper number of significant figures. So you're not really making your measurement worse. That's a very common mistake that people make. They just feel like, yeah, it's not that important. I'll just slop off that sort of zero, if you will. But it does make a really big difference in terms of the quality of the measurement that you're making or that you're looking at when you do take off that zero. Any questions on that? By the way, if you take measurements of anything that is digital, you should always record all the numbers. They're usually important. Usually in your cases, like the balance or the scale, you usually have a digital one. And that's also a very common thing that people do is they sort of just drop off numbers and go, I'll just record whatever it is. The 52.365 grams, not that important. I'll just call it 52, So again, and when you do that, you're making really your measurements a lot worse. Any questions on that there? Yeah.
How many numbers? So like if you have a large number that has, let's say, what did you use right now?
With the 52? I don't remember getting all 52.324. How's that? Uh-huh.
Three digits after. But say you're using like a calculator or whatever, and you
Yeah.
have 6 digits after the decimal. You want all those numbers?
So we're gonna talk about that. I think your question here in just a second, but typically speaking, if you're doing something on the calculator, you don't want to round too much, especially if you're going to take that number and kind of use it in another calculation. So if you're going to like, if you did a calculation, got a number, and you want to take that number and then do another calculation with it, and then maybe you're getting another number and do another part of the calculation. Typically speaking, you never really want to round to the very end. And then you should clean it up to the right number of significant figures. And we're going to talk about how to determine the proper number in just a sec. But that's a really good thing to keep in mind is, you don't want to really round, and we'll talk a little bit about it in just a sec, but basically as you round, you're kind of moving yourself further and further away from the correct answer because you're basically doing what we're just talking about here. You're kind of like making your measurement worse and worse and worse. So you're kind of moving yourself through. So definitely on any calculations where you're kind of doing multiple steps and maybe you're getting numbers and continuing on, you definitely want to wait to the end around. Now, if you got like 400 digits in your calculator, do you have to write them all on the paper? Probably not, but I would take it to a good number of digits to be safe and then kind of clean it up at the end. Yeah. Other questions? Okay, so our fish. So let's talk about actually how to properly, and again, just make sure everybody's on the same page, how to properly count significant figures. So first off, any measurement that has a non-zero are significant. So any number that pretty much is a non-zero is a significant figure. That actually is where you want to start counting. So you want to go left to right on the number, and the very first non-zero that you hit is when you should start counting significant figures. So if we look at 1, 2, 3, 6 here, here's our very first non-zero. That obviously are all non-zeros. So this guy would have 4 significant figures in terms of its measurement. Now, we have 3 different types of zeros, and they sometimes give people a little bit of trouble. The first type of zero are what are referred to as leading zeros. And those are all the zeros that come right before you hit the very first non-zero number. So if we look here, all these zeros that come here, we would not count because we have not hit a non-zero yet. We would actually start counting right there at the 2, and the 2 and the 5 would be significant, and this guy would have 2 significant figures in that particular case. So you could have like 1,000 zeros before you hit that first non-zero. They would all be not significant again until you start counting. The second type of zero is one where we have zeros that are basically trapped between 2 non-zero numbers, and those are significant always. So again, following left to right, starting at 1, which is our first non-zero, the 2 zeros are trapped, and the 5 at the end is significant. That would give us 4 significant figures here. Now, the very last type of zero is really the one that gives people sometimes a very hard time, and those are zeros that come at the end of a number. And when you have zeros that come at the end of a number, they may or may not be significant. What determines whether or not they're significant is there a decimal anywhere in the number? So if you got a decimal point in the number, it makes every single zero at the end significant. If you do not have a decimal, then they are not significant. So when we have 100 written like the first one here, that would have how many significant figures? It would have one. It's actually just the very first one there on the left. The zeros that come at the end are not significant. If I wrote 1.00, it would have 3 significant figures. Again, with that decimal there, it's going to make those zeros at the end significant, and it would have 3 significant figures. Now, if I wrote 12,000, how many significant figures does this number have? It does have 2 significant figures. So the answer may be an earlier question, which one is the estimated digit or uncertain digit? That is both answers. So the 0 or the 2, right? So again, this one has 2 significant figures, which means these would be the 2 significant figures, which means by definition, the 1 would be a certain number and the 2 would be your uncertain number here, or the estimated digit. So the 2 actually in this particular case would be the estimated digit, or the uncertain digit would be that 2 that is there. And again, this is an example, as we were talking about earlier, you can see it is not the last number written, but in this case, it is the last significant figure. So when you're ever asked about an estimated digit or anything like that, again, always the last significant figure. If I wrote 12,000 like this, it would have how many significant figures? It would have 5. The uncertain digit would be, it would now be the 0 right here at the end would be your uncertain digit. Yeah. Yeah.
So the zeros for the first example weren't significant, but then if there's a decimal, they are.
If there's a decimal point in the number, the zeros that come at the end are significant. So I think I have an idea, maybe what your question might be. So you might be asking, like, or some people might be asking, but don't these zeros come after the decimal point, right? And the answer to that question is we haven't started counting significant figures yet, right? Because technically speaking, this is a 0, so we don't count it. That's a 0, we don't count it. That's a 0, we don't count it. That's a 0, we don't count it. So we wouldn't really start counting significant figures until we hit that number 2 right there, which means even though technically speaking, those zeros come after the decimal point, they are not trailing zeros. They're actually leading zeros because we haven't started counting our first significant figure at this point. So this would be 2 significant figures. Now, if we did this guy, this would have how many significant figures? It would have 4. Same reason, we're not counting sig figs until we hit here. And now we can start counting. The 2, the 5 would be significant. Now these 2 zeros are going to be significant, even though they're not nowhere near the decimal, but there is a decimal in this number, and this guy would have 4 significant figures. Exactly. So really, the leading zeros are the zeros that come before you hit that first non-zero, and they're never counted. And it's basically not until you hit that first non-zero that you should be counting, basically. And at that point, you'll run into really only 2 types of zeros: zeros trapped or zeros at the end. Question or? The rules for any number is you want to start on the left and go this way until you hit the first non-zero number. And that's when you should start counting. Yeah, that's when you should start counting. So let's just say we took a crazy measurement like 0.00300500043200000 centimeters. Okay. How many significant figures does that have? I have no idea. I just wrote it. If he made that measurement, I'm not sure what you're using to make that measurement, but let's just pretend. All right, so let's just follow our logic here. We're going to start left to right, right? So we're going to start this way. I'm not counting until I hit here, right? That's really where I should start counting my first one, which means pretty much all those zeros I just passed, I'm not going to worry about. This would be really, I'll put a 1 here. That's my first significant figure, if you will. All right, I'm going to lose track. So these are 2 zeros that are trapped. Are they significant? They are. So that is 2, 3, 4 more trapped zeros here. 5, 6, 7, 8, 9, 10. Now we have zeros at the end, right? Are they significant? They are significant. Again, nowhere near that decimal, but they are here. I lost track. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and a lucky number 15. That's quite a measurement you did there. I'm not sure how you did that, but those would be significant. Everybody follow? Yeah. Okay. Any questions on that there? Okay. So let's talk a little bit about rounding, which I think was a question as well. Again, in general, let's just talk about general rounding rules. When we do round, it's normal sort of procedures. So if sort of the digit where you're going to end your number, the next number is 4 or less, we just sort of drop the rest of the numbers. So in this particular case, if we wanted to go to 3 significant figures, we would start counting here at the 3, which is our first non-zero. That would be 2 significant figures. That would be 3 significant figures at the 2. We would then look at the 4, which means we essentially will just drop the rest of it because it's less than 5. And we should round it to 3.72 in this particular case. Questions on that one there? Anything above 5, we drop the rest of the numbers basically and round up 1, right? So here again, if we were going to 3 significant figures, that is number 1 in our significant figures. This and this guy would also be our next 2 significant figures. That means technically we would be looking at the 6, which means we should round up and we should end up at 5.01, which would be 3 significant figures. Any questions on that? Yeah. It's just a random thing. We could have said 2 or 3. So where this would obviously come into play is if you're doing calculations, which we'll talk about here in just a second. You know, at the end, you might go, okay, my answer should be 3 significant figures, or my answer should end up at 2 significant figures. So you may have to do some rounding. As you probably know, right, your calculator doesn't always give you the number in the proper sig figs, and you have to get rid of some numbers and stuff like that. It is really important as well. So for example, if we had, say, 13,333 and we wanted to go to 2 sig figs in this case, what would be the answer? 13,000. Anybody for 13? All right, so let's take a look at both of these. These are 2 common answers that are given. Let's first talk about sig figs. This guy has how many sig figs? Does have 2 sig figs, right? How many sig figs does this guy have? It does have 2 sig figs. Again, no decimal written, which means we start counting at the 1, and then the 3 is significant. The other guys are there. Now, when you do round, this guy would not be so good, right? So for example, if I owed you $13,333 and said, I'm going to pay you 2 significant figures, here's $13. I'm not going to get out of the room probably very well there. There's a very big difference in the meaning, right, of 13 versus $13,333. So you don't want to do what I sometimes call extreme rounding. Sometimes people are so focused on getting the right number, significant figures, is they do some extreme rounding where basically they change the meaning of the number. You never want to do that. Now looking at 13,000, that has 2 significant figures. 13,000, maybe you give me the $333 teacher discount, right? You know, 13,333 is pretty much the same value. We really didn't change the value. So you always want to be really careful and make sure that, all right, so you never want to change the actual meaning of the number when you do that. And again, it's a very common thing that people will sometimes do when they are trying to get the right sig figs. More importantly, let's talk about the significant figures in the calculation. There's basically 2 types of calculations that we do. We either multiply and divide, or we add and subtract. So first off, if we multiply and divide, what we're looking at is significant figures, and we're looking at the one that has the least number of significant figures is the number of significant figures that your answer should have. And that is really based on what we were talking about earlier, that, you know, really the least sig figs and all that kind of stuff is probably your worst measurement. Your calculation, again, is only going to be as good as really that worst measurement that you have. So if we were to do this calculation on our calculator, again, our calculator will probably not give us the right number of significant figures. The very first number here, 6.038, has how many significant figures? It does have 4 significant figures. 2.57 is 3 significant figures, which means our answer should end up being 3 significant figures, right? And if we look at that, that would take us to the 5 here, the second 5. And we would look at the number after, which is a 1, which means we'll just drop it, and we should end up with 15.5, which would be 3 significant figures in this particular case. Any questions on that one there? Now, adding and subtracting is a little bit different. When we add or subtract, what we're looking at is actually decimal places, and it's still the least number of decimal places. So your answer should end up with the same number of decimal places as your number with the least number of decimal places. So if we add up all this good stuff here and put it in our calculator, and figure out what I did in my calculator, 9.33 plus 1.4 plus a 10.733. That gives us on the calculator 21.466. We should end up where on this answer? So let's take a look. So we are looking at decimal places here. First number has 3 decimal places. Next number has 1 decimal place. Last number has 3 decimal places, which means we should end up with 1 decimal place. We do look at the 6, which means we need to round up, and we should end up with 21.5 in this case. Any questions on that there? Now, sometimes when you are doing calculations, you may be doing multiple steps together, and you really do need to kind of keep track of what you're doing. So for example, you know, if you were doing something like this, 323 times 1.4 divided by 3625. When we would do this math here, the first thing we typically would do is the guy in the parentheses there, which means we're multiplying, which means technically speaking, the answer we get on top there should have how many significant figures? This one is 3 significant figures, right? This guy is 2, which means when you get the answer for the top part of it, it technically should be 2 significant figures, right? The next thing you would do is take that answer up on top and divide it by the guy on the bottom. And again, we would be looking at significant figures. So that is 4 significant figures on the bottom, 2 on the top, which means our answer should end up at 2 significant figures in this case. So if we took 323 times 1.4, technically speaking, the number you get up on top is 452.2, which technically should be 2 significant figures. Would I personally round at this point? The answer is no. I would just take that whole number and then divide it by 3625. And that gives me an answer of 0.124744827 on my calculator. That means we should end up, if we followed our rules, to here, and we should end up with 0.12 in terms of it. So, you know, sometimes you do multiple things. Sometimes you cross over, do both things together, add, subtract, and maybe multiply, divide. You do want to keep track of it. And as we were talking about earlier, you really don't want to round to the very end. It's really good practice not to do so. In a lot of cases, you know, if it's not a lot of steps, you probably will still be relatively close if you did round, but it's not really a good idea to do so. So sometimes people will keep all the numbers. Sometimes people will, you know, for example, on the top there, if I know it's 2 significant figures, maybe keep a few extra digits there as you go through the calculation if you want to round a little bit, but definitely I wouldn't do significant rounding until the very end and you kind of clean everything up. Any questions on that there? Now, there are exact numbers and there's measured numbers. Exact numbers, I think we might have talked about as well the other day. Exact numbers are those ones that are basically things that we count. Are there definitions like 12 inches is 1 foot and things like that? When we're doing calculations that involve something that is classified as an exact number, we don't have to worry about the significant figures. They technically could have as many significant figures as you want, which means when we do calculations that involve those, we really don't have to worry about the number of significant figures. So a lot of times if you're doing something, as we'll do a little bit later on in this chapter, like conversions, and all you're really doing is conversion using conversion factors, a lot of times you're pretty much multiplying and dividing, which means that your original number is a lot of times the right number of significant figures your answer should have. Not 100% of the time, but in a lot of cases, it is like that. Any questions on sig figs? All right, let's talk a little bit about scientific notation. Oftentimes in chemistry, we have really large numbers, really small numbers. They have a lot of digits in it, a lot of zeros. So clearly, if you're doing a calculation there, which Avogadro's number up there, you probably don't want to carry around the however many zeros there are, 19 zeros that are in that number. You're probably going to lose them. So we really do use scientific notation to help us handle these really large numbers, obviously really small numbers as well. By the way, this number here would have how many significant figures? Yeah, it's just these guys, right? We would start counting at the 1 and it would be the 6 and the 6. All those zeros that come before are not significant because we haven't started counting until we hit the 1 at that particular point. When we do write something in scientific notation, it does have this sort of general form of n times 10 to the n, where n is a number between 1 and 10. Not 1, not 10, but a number between those two numbers. And this number up here can be either positive or negative, depending on really which way you kind of have to move the decimal point to get your number between 1 and 10. Now, for example, if we had 3, 2, 5, 6, if we wanted to turn that into scientific notation, although it's not written here, and this would be one time where we would assume that the decimal would be here, even though it's not written. One place to the left gives us 325. That is not between 1 and 10. One more place gives us 32.5, which is not between 1 and 10. And one more place there gives us 3.256 times 10 to the 3, how many places we moved. If it's a large number, you'll have a positive exponent. If you have a smaller number, we would go 1 place, 2 places, 3 places to the right and end up with 1.30 times 10 to the minus 3. Negative exponent means that it is a smaller number. Whenever you write a number in scientific notation, all the number before the times 10 part, they're always significant. Which means when I wrote this number in scientific notation, how many significant figures does it have? It does have 4. All the numbers comes before the times 10 part, these guys right here. And that's good because my original number had 4. So that's why we kept all the numbers there. We shouldn't lose any significant figures as you go from scientific notation to decimal form. Same thing here. This number has how many significant figures? Does have 3. Again, it has a decimal and the 0 at the end, so it's all good. And that's good because my original number here had 3 significant figures right there. So again, that's why we kept the 0 at the end, because it was significant. So when you write a number in scientific notation, you never want to lose the number of significant figures. You want to make sure that you maintain it. Now, for example, let's do, and we want 3 significant figures here, right? So if I want to write this in 3 significant figures, where would that take me to? 3 significant figures, this is 1, 2, and 3 here, right? What should the answer be? If I write 12, 0, 0, 0, that's how many significant figures? It's only 2, which is not good, right? So that didn't work. You know, if I drop this 122, that is 3 significant figures, but the problem with that is doesn't mean the same thing anymore, right? So that's no good. That's no good. If I did 12,000 here, put a decimal at the end, that would have 5, so that's no good. So there are certain situations that you may need a certain number of significant figures in your answer. And really the only way you could do it is to write the answer in scientific notation. The nice thing about scientific notation is you could control how many significant figures you need. So if I needed 3 significant figures here, I could just write 1.22, again, going 1, 2, 3, 4 places times 10 to the 4. And now I have 3 significant figures, right? If I needed 2 significant figures, I could just write 1.2 times 10 to the 4. If I needed 4, for example, you could literally control how many significant figures you want or need by writing a number in scientific notation. And again, in some cases, it may be the only way to actually get a number to the correct number of significant figures is to write it in scientific notation. Any questions on that there? Yeah. I was just adding zeros to get me to 4, but you would be correct. If we wanted 4, I probably in this example would have kept the 2s. Yeah. Are we talking about this? Yeah, this part? That part is the basic setup of scientific notation. It's basically a number between 1 and 10 times 10 to the whatever number it is. So it is always times 10. The part that changes is the top number based on how many places you had to go to move the decimal place. Other questions? So again, the number of decimal places moved really determines whether or not it's going to be positive or negative. So take a second here. Why don't you write each of these in scientific notation, proper scientific notation, with the right number of significant figures. Yeah. They're not. They're just from PowerPoint. So sorry about that. Yeah. None of these are negative. They're just like PowerPoint through the little dash in. The same amount that it started with. How's that? Yeah. So take a look. So starting with the first one here, we got to go to the left there, 1 and 2 places to get us to a number between 1 and 10. In this particular case, it would be 5.68762 times 10 to the 2. Again, originally 6 significant figures. We don't want to lose any here. So we do have 6 significant figures over here, which is why we keep all the numbers that we see. In this case, on the next one, we need to go to the right, which is 1, 2, 3, 4, 5, 6 places to the right. That gives us a 7.72 times 10 to the minus 6. Again, small number, negative exponent. Again, even though it has all these zeros at the beginning here, we don't start counting until we get here. That's 3 significant figures, which we also maintained here when we turn it into scientific notation. This guy should end up being 1.25 times 10. Again, 1, 2, 3, 4 places over. In this case, I dropped the zeros because the original number had how many significant figures? And now I have 3. If I left the zeros there and put 1.2500, I would have 5 significant figures, which would be too many. So in this case, we do want to drop those zeros as they're not significant and transfer it over. Lastly, here, we just need to hop 1 place here to the right, and that will give us 1.35 times 10 to the minus 1. Any questions on any of those? Yeah. The goal is it needs to be a number between 1 and 10. So it's got to be a number between 1 and 10. So for example, if we were doing say this original number here, which is 568.762. If I move it just one place, technically speaking, I'm now at 56.8762, which is not between 1 and 10. I need to go one more place that gets me to 5.68762, which now is a number between 1 and 10. So you want to move the decimal place whichever way to get yourself to a number between 1 and 10. However many places that you moved is what ends up over here up on top in that particular case. Yeah. Other questions on that? And obviously, like I said, if it's a big number, it'll be a positive, or if you moved it to the left, it'll be positive. If you moved it to the right, it'll be negative, or it's a small number. Any questions on scientific notation? The question of, do you have to write scientific notation or give everything in scientific notation all the time? The answer is no, you do not need to do that. You can if you want, but you don't have to give everything in scientific notation unless this question specifically asks you to do so. But you do need to give everybody to the right number of significant figures when you do it. All right, let's go. Let's see if we can kind of go backwards. Now, more important than writing things in scientific notation is actually using your calculator in scientific notation, right? So let's just make sure everybody knows how to properly use your calculator in scientific notation. Every calculator should have an actual exponent button, a dedicated exponent button that looks like EE, looks like EXP. Or if you got some of the newer ones, you might actually have a button that looks something like that, times 10 to the n. These are your typical exponent buttons on your calculator. If you have this button, we'll talk about you in just a second, but we'll start with these two buttons here. These are actually your exponent buttons. So if you remember, scientific notation looks something like this. So if we had a number like 6.25 times 10 to the minus 6, and I want to actually put that into my calculator correctly, you would go 6.25. You then would hit your exponent button, either the EE button, the EXP button, one of those two. And on most people's calculator, it'll put a 6.25. It'll probably put an E, or it may do like a 6.25, maybe pop up a couple of zeros up high, maybe with a little times 10 on the bottom or something like that. When you hit the EE button or the exponent button, that represents the times 10 part of the number. So that part of the number is represented by that EE button, which means you do not need to hit the multiplication button. You shouldn't. You shouldn't be doing anything like the second log or inverse log button. You shouldn't be using that log button at all. Shouldn't you be using the caret or anything like that? That's all you have to hit. It's -6, which means you then want to use your negative button. And on most calculators, two options on that. Something looks like that, or something that looks like that, not your subtract button. So then you would hit your negative button. That would make it a negative. And then obviously you would hit 6. That would go 6, and that would go 6. And that's the proper way to punch in a number in scientific notation in your calculator. Again, at no point did I hit the multiplication or anything like that. If you are using this button on your calculator, maybe like the second button or shift, and that is how you're doing it, it is absolutely wrong. You should not be using those buttons for scientific notation. Any question on that there? Yeah. Yeah, it will work sometimes. It depends, but you definitely want to use either this button, or most calculators will probably have this button here. And if you have that button, that actually is your exponent button on that calculator. Let's talk about if you do have that button. If you do have that button, it typically will have this button somewhere on there, and you know it because you usually will have a dial on your calculator, like a circle. Those are usually the ones that have that sort of button. Yeah. No, it's okay. No worries. It's all good. That's why we're figuring out where our buttons are. So if you do have that little dial, you usually have this times 10 to the n button on it. And you basically got to do the same thing, except that you have to, because of the way the calculator is programmed, you got to lay up a parentheses first and then go 6.25 You're then going to hit the times 10 to the n button. And on your calculator, what that will show usually is parentheses 6.25. The usual pop it times 10. And you'll find like a blinking cursor up there on top. What you then need to do is the rest of it. So then you would hit your negative and 6. And what that will do is it'll go 0.625 times 10 to the negative 6. You will still have your blinking cursor up on top at this point. That is where the circle button comes into play. There's this side right here. You hit that. That will bring your cursor down so that you could close the parentheses properly, and you could close the parentheses at that point. So you just got to do a little bit more work. If you have this button, historically, those things are programmed. I won't say wrong, but wrong. So for our purposes, and if you don't do the parentheses around the numbers, if you have that type of button, you will get the wrong answer because your calculator is going to do different math. It thinks you're actually doing two separate numbers, even though you're trying to do one number together in scientific notation. So that's the extra sort of thing you have to do if you have sort of a new one. Usually the two-tone type calculators, newer ones, have that sort of button. You got to kind of do that. And they usually have the little wheel on it, and those are usually the one. If you have an EE button or EXP button, you're in good shape. You can just hit that button. You don't have to worry about parentheses. Everything will work out all right. But you definitely have to do the parentheses on the other button there. Any questions on that there? So why don't we try one here just to make sure. Do you have a question or? What's that? I'd be very surprised if you didn't have one of those three. Most of the cases that you should have most for sure. If not, you could come bring it to me and we'll find it. But I haven't seen a calculator that doesn't have one of those three buttons usually on it and stuff. Yeah, you could put your calculator in scientific notation if you want, but to actually punch in the number, you usually have to use one of these three buttons for sure. So if you're not sure where your exponent button is, just bring it up to me after class. We'll find it together. But for sure, I haven't seen a calculator that doesn't have one of those three. I could be wrong. Maybe they make new ones, but usually they have one of those three for sure. So why don't we try one here just to make sure? Let's just say let's say we took 3.25 times 10 to the minus 6. And let's divide that by 1.2 times 10 to the 13. And then let's do 6.334 times 10 to the minus 9. And we'll multiply that by, we'll do 9.8 times 10 to the, let's do negative 4. All right, take a second, punch that in, use your exponent button. All right, let's take a look at the first one. So again, I'm just going to kind of write how you should perhaps punch it into your calculator. So starting on the first one here, again, you should go 3.25. You should hit your exponent button. Again, that represents the times 10 part, so no multiplication or any of that type of stuff should be hidden. You then should hit your negative button and then 6. You then should hit obviously the divide button and put the other number in the same way, 1.2 exponent button. And this is just a positive 13, so no negative needed. And then your equals. Yes, so that is really the right way to do it. Again, you don't see any multiplication, carets, or any of those other weird things. 3.25 exponent negative 6 times divided by 1.2 exponent 13. On my calculator, I end up with 2.7083333. And you don't want to forget the other part that people sometimes forget, times 10 to the minus 19. Sometimes they're kind of hidden in the corner there. Yeah, so it's very common. People will forget the times 10 part when you do report it. Or you may have a calculator that says E to the minus 19. And obviously that E represents the times 10 part when you turn it in that. Should I leave all those numbers on this? That's a good answer. So we are dividing here. So we should be looking at significant figures. First number has how many significant figures? It does have 3 significant figures, these 3. Second number has 2, which means my answer should end up with 2, which takes us here. So really, we should report this as 2.7 times 10 to the minus 19. And that's the right way to report it. By the way, if you do have a calculator with an E, please do not write your answer like this. It just annoys me. Yeah, so don't do the transfer it back to times 10 to the minus 19 when you're writing the answer and stuff like that. Any question on that then there? Second one, same deal. You're going to basically go 6.334. You're going to do your exponent button. You're going to do your negative button. And you're going to do a 9. In this case, we're going to multiply. So we're going to hit the multiplication button. 9.8 exponent button. And this one's also negative. So negative and 4, and then hit equal. And in this particular case here, 6.334 exponent minus 9 times 9.8 exponent minus 4 there. On my calculator, giving me 6.20732 times 10 to the minus 12. Again, we don't want to forget that part. Here we are multiplying, so looking at sig figs, that is 4. And that is 2, which means in this case also should end up at 2 significant figures. And that would give me 6.2 times 10 to the minus 12. Question on how to use your calculator, probably more important than most things, to properly put scientific notation in your calculator. You definitely want to make sure you always use the exponent button. Also a reminder that sometimes your calculator will give you the answer in scientific notation. Sometimes it will not. You can, like I said, put your calculator into scientific notation in most cases, but that's totally up to you. Any questions on that there? If you're finding yourself when you get the answers that, this part of the number looks good, but this part doesn't look so good, it's like just off a little bit, this part looks good, but this part doesn't look good. That usually is a result of how you're punching it into your calculator. It's usually a result of not punching it in correctly. Either very commonly, people always want to add the multiplication button in between or something like that. So, don't do those extra steps. Any questions on that there? Okay. All right, question on scientific notation, significant figures and calculation. Very good. Okay. Then we're going to talk about, if we get there. Oops. All right, we're going to talk about writing conversion factors. So conversion factors are really just fractions. They're really 2 fractions, and they really come from an equality. So an equality really is 2 things or 2 values that are on different scales or units, if you will, and they do represent the same amount of something. So when you say you have 100 pennies equals $1, it does represent the same amount of money. They're just on different units. There are 12 inches and 1 foot. Again, those are equalities. They represent the same amount of length, if you will, or distance, just in different units. From any sort of equality, you could write 2 conversion factors. So for example, for this one here, we could say for 12 inches up on top, 1 foot on the bottom, or 1 foot up on top, 12 inches on the bottom. Will we use really both conversion factors in a problem? The answer is probably not. Otherwise, you'll undo it. You will choose the conversion factor that really suits your needs. And we do a process, as we'll talk about, which is known as dimensional analysis. And that's just a fancy way of saying we do conversion factors where we show basically the units canceling each other out. So for example, if we were starting with 1 unit, like unit A, and we wanted to convert it to unit B, we could use a conversion factor where unit A would go on the bottom, unit B would go up on top. Although this first guy is not written as a fraction, you could think of it as a fraction where unit A is up on top. And whenever we do dimensional analysis or conversion type problems, opposites always cancel. So basically what we're doing is we're multiplying everything that's on the top and we're dividing by what's on the bottom. So ultimately what we're doing is we're dividing, taking units A on top, divided by unit A on the bottom. That equals 1, just like if you divided 2 by 2, it also cancels out. So the units here cancel, and we're left with the units we're looking for. So a real example is if we started with 425 inches, and we want to know how many feet that is, we would start with 425 inches. Again, we want to go opposite. So although it's not really written as a fraction, inches are up on top, which when we go to our two conversion factors over here, which one should we use? One on the left or the one on the right? We should use the one on the right as it has inches in the opposite location on the bottom. We would use that as a conversion factor, 12 inches on the bottom, 1 foot up on top. Essentially, we're going to divide inches on the top by inches on the bottom, so those units cancel each other out. We would then take, basically multiply all the numbers that are on top, which is 425 times 1. We would then come back and divide by the bottom, which is 12. And that gets us 35.41666667. The units that are left at this point are feet. And I'm sure you know we should not leave it with that many digits, right? So this is what we were talking about a little bit earlier. This is an equality, right? That falls under an exact definition, which means we're not going to be concerned about the significant figures in this particular one. That means that the only significant figures we have is our original number, which has how many? 3, which means our answer here should actually have 3. So we should end up with 35.4 feet. Question on that there. So that's basically what dimensional analysis is. It's using these conversion factors. We could write a conversion factor for anything that is an equality. So we could get them for all kinds of places. So for example, if we were driving 65 miles per hour, those are basically 2 units. 65 miles per hour basically means you could drive how far in an hour? 65 miles is basically what that means, right? So you could go 65 miles in 1 hour. Or if you drive in 1 hour, you could go 65 miles. So those are the 2 conversion factors that we could use to solve a problem, right? So, if we had to go, we had to go 558 miles to spring training in Arizona, which doesn't seem like it's going to happen. We can figure out how long that would take us, right? And in this particular case, miles would be up on top. Again, not really written as a fraction, but the miles are up on top. That again means that we should use a conversion factor over here to help us out. And the miles will cancel each other out. We'll take our 558 miles divided by 65. Maybe if we drive to Florida, we'll be in spring training by then. It'll be 8.58 hours to do so. It's a little bit longer than Arizona. All right, you'll find yourself in New Mexico at that point, just so you know. Then you can keep going, it's all right. Any questions on it? By the way, 3 significant figures here. Actually, that's incorrect here. This is really not a true conversion factor. 65 miles per hour. It is specific for this problem. So we actually should look at the 2 significant figures here, which means really we should actually end up with 8.6 hours would be probably the proper sig figs in that particular case. Again, 3 and 2 in this particular case. Sometimes you are given sort of conversions that aren't really conversions all the time. Like, there's always 12 inches in a foot, no matter what the situation is. Clearly something like that, if you're driving, is not truly a true conversion factor, right? Because it's not always driving at 65 miles per hour. Now, we do have some different types of units, as we talked about. We talked about our English and our metric units. And when we use a conversion that comes from an English to English sort of equality, and we use it in a conversion, we don't have to worry about the significant figures. It's considered an exact number. If you use a metric to metric equality or conversion factor, it's also considered an exact number. It is, though, when you cross over from metric to English, you should look at the significant figures in those conversions when you're doing the problem. The one exception would be this guy. There's exactly 2.54 centimeters in 1 inch. You could consider that an exact sort of conversion factor. But everybody else you should look at. So for example, if you were using this conversion factor, this would give you 3 significant figures in that calculation, and you should take that into account. I will say probably in most cases, even if you needed to in a metric to English sort of conversion, take it into account. Probably that original number is still probably going to be pretty close to the right number of significant figures that we did. So, you know, if we were 170, we'll do 175.5 pounds, and we want to know how many grams that would be. We would do 1 pound on the bottom and 454 grams up on top. The pounds will cancel as they divide each other out. We would end up with 175.5 times 454. That would give us 79677 grams. In this particular case, since this is a crossover metric to English, this is where we would look at our significant figures in this number, not the one. The one is just basically 1. So 454 would have 3 significant figures. This would have 4 significant figures, which means technically we should end up with 3 significant figures here as we're multiplying and dividing, and that would be 79700 grams. So in a rare case, not really rare, but you know, if you do use some type of conversion factor that is that crossover one between metric to English, you should take it into account as conversion or sig figs, and you know, it may actually be less. Yeah. Yeah, so if your question is how you cancel mount it, it's basically opposites cancel. So like in this case, when we just start with one number by itself, it's technically not a fraction, it's not written as a fraction, you know, like when we started with the 175.5 pounds. It's really just a number, but any whole number really you could think of as a fraction by kind of putting it over 1. If that helps you visualize that pounds are up on top, then that will help you visualize pounds should go on the bottom when you're using the conversion factor. And it's really important to do it. So for example, we had the miles per hour, right? Let's just say, you know, we were driving that 65 miles over 1 hour, right? In this particular case, we actually have 2 different units, right? And if we write it like this, we could clearly see miles are on top, right? And hours are on the bottom. So maybe we wanted to know how many miles that was per second, right? And that will help us figure it out. By the way, in 1 hour, there are how many seconds or how many minutes? Now there's 60 minutes. And if I did this conversion, hours are opposite, right? The guys, hours on the bottom, hours up on top. If I stop the calculation right at this point, what units am I in? Miles on top, right? Per minute, right? Now I wanted seconds, so I can now clearly see by setting it up like this, minutes are on the bottom, which means up on top should go a minute, and that should give us 60 seconds on the bottom. Again, the minute on top and minute on the bottom would cancel, leaving me miles up on top and seconds on the bottom. And that would give me the units I was looking for there, miles per second. So that's really what dimensional analysis is, what I just did there. And you could clearly see where the units are. It is a super common mistake when people have a unit like this and they want to convert it. They're not really sure where the time is. So they'll end up, instead of dividing like we should be here by the number, they'll have to be multiplying and stuff like that. So if you write these things like this, where you could clearly see where the units are and just think opposites cancel, you could clearly see where you need to put your conversion factor so that the units will properly cancel each other out. By the way, mathematically, if I was going to solve this, I'm going to multiply everything on top. So 65 times 1 basically. In a problem like this, you can multiply as many numbers as you want across the top. You should hit equals, by the way. You're then going to go back and divide by all the numbers that are on the bottom. Now, this is also a common calculator error that people do. They want to put it all in at once. And if you want to be safe, the best thing you could do is multiply everything across the top, hit equals, divide by the first number, which would be 60 in this case, hit equals, divide by the next number and hit equals. And you always get the right answer. if you try to put it all in at once into your calculator and you're not very proficient with parentheses, you will get the wrong answer. So if you ever have a situation where you're doing a lot of multiplication, you got to come back and divide by a lot of numbers. The very simple and easy way that you always get the right answer, you take as many numbers on top and multiply, just hit equals at the end, divide by the first number, hit equals, divide by the next number, hit equals, however many numbers there are, and keep hitting equals, and you'll always get sort of the right answer. Any questions on that there? Okay, we'll lay it up there for today.